Hello, today I'm gonna talk about energy in simple harmonic motion, which is very similar with the gravitational potential energy. And you see there were two different type of energy you have learned so far, I believe. The first one is a kinetic energy, which is a 1/2 times a mv square. And the other one is a potential energy, gravitational potential energy, which is a mgh, right? So today I'm going to introduce new potential energy, but this is for spring. This formula is 1/2 times k x squared. So that means if you increase your x, so in other words, if you either stretch or compress your spring, your potential energy is increasing. Like you lift an object, from ground, and then you lift an object upward, right? So this is a h, right? So increase your height, you increase your gravitational potential energy. Likewise, so let's assume this is equilibrium position. If you stretch more and more, you store more spring potential energy. And here you again have a energy conservation. So this, brown line is your total energy, right? When you have a maximum stretching, you have a maximum blue potential energy. Like you have a, ball at the highest point here, you have a max potential energy. But once you drop it, what happened? Your potential energy is decreasing, and then your kinetic energy is increasing, right? Because why? Because your velocity is increasing. You have the same process. Here, the V here is 0. So your kinetic energy here, which is a green part, is 0. But you have a maximum stretching, so your spring potential energy is a maximum. At the midpoint, what happened? Your speed is maximum, and then your potential energy is minimum because x is a 0. And here again, you come back to maximum kinetic energy and minimum. Oh, here at the end, the object will stop. So your V here is 0. So your kinetic energy is a 0, but the potential energy again, maximum. So this is the same energy conservation that you learned from potential energy conservation. Okay? So for the mass of a spring, when the object is at rest, the potential energy is maximum. So at both ends here and here, your potential energy is maximum. The blue one is maximum. But at the midpoint, because again, x is 0, your potential energy is 0. With the kinetic energy, your velocity here is max, right? Your velocity is max. So kinetic energy here is max. So in other words, the green line has a maximum kinetic energy, right? So again, your spring potential energy is 1/2 mkx squared. So your total energy, like you did before for gravitational energy, there your total energy was what? 1/2 times mv squared plus mgh, right? But here you have the same kinetic energy, but instead of a gravitational potential energy, you have a spring potential energy. And the sum is always a constant. So what is a maximum potential energy? Maximum potential energy is same as the total potential energy, total energy, which is 1/2 times Ka squared. So here you see the only differences I see here is I changed x to a because the maximum value x is a. So the maximum potential energy is simply 1/2 times Ka squared. And then what is the maximum kinetic energy? Maximum kinetic energy is 1/2 times mv max squared, where at the midpoint, right? And then you remember for the simple harmonic motion, what is a Vmax? You remember that's what we did last time. It's a K times a, I'm sorry, V is A times a omega, which is a 8K times a, I'm sorry, it's 8, right? Vmax is 8 times omega, which is 8 times a 2 pi over T, or 8 times a 2 pi F, right? 8 times a 2 pi F. So in other words, K max is a 1/2 times a M, V is a 8 times a 2 pi F square, right? That's a V max, right? But the thing is, your energy is always conserved. This is also E total. And then this is also E total. Why? Because here, your total energy is the maximum potential energy plus kinetic energy, but here, kinetic energy 0. Here, your total energy is kinetic energy plus potential energy, but this is 0. But anyway, your total energy are the same, so this equals to this, right? So we'll talk about this one later. So now we have a very conceptual, simple conceptual example, right? You're at the playground here, undergoing simple harmonic motion, moving back and forth, right? Describe the changes in energy. Again, here, highest point, highest point. So you have a maximum potential. And then at the midpoint, your potential energy is 0. But the speed at the midpoint is maximum, so the kinetic energy, blue one, is maximum here as well. But the total energy, which is the sum of blue and then green, are always a constant. Right? You can also read the textbook very carefully. And then, as I said earlier, this is what? Max kinetic. And then this is a potential max, right? Which is always the same as what? E total. So then you can simply say these two are the same. This is very important. You have to know, memorize. It doesn't, you don't need to memorize, right? So as long as you know what is the kinetic energy, potential energy for springs, right? So then you cancel half, both side, right? And then, so left side is M, V, max square. But again, V max is what? 2 pi FA, right? 2 pi F pi F A square equals what? This one, K A square. So this is A square, so you cancel A. So the left side is what? M 4 pi. Let me do it again. It's just to use the 2 pi F. 2 pi F square is a K, right? So that means you have a divided by both sides by M, so 2 pi F square is K over M. So 2 pi F equals root K over M. So now your frequency is 1 over 2 pi root K over M, right? So this is a frequency of a simple harmonic motion. You can also express this one in terms of a Ty, 1 over T is a 1 over F, right? Or F is a 1 over T. So then you can say 1 over this one. So just, take the reciprocal of this F value, which is a 2 pi K over M. M over K is your period. Again, I'm not going to ask you to memorize this formula, but you must know this formula, and then you must know how to drive this one. So how to get this one I? You have to use the energy conservation. Maximum kinetic energy equals to maximum potential energy, right? So if you go over this process, it's just, 3 or 4 times, you can do it like in 5 seconds, okay? So now let me talk about this formula a little bit more carefully. So the frequency of a spring is proportional to root k spring constant and inversely proportional to mass. Think about why. Because let's assume, k is a spring constant, right? So if you increase k, what does that mean? You're gonna use a stiff, right, strong spring. So then what happened? The oscillation. If you have a very, very strong spring, and once you release it, spring move back and forth really quick, right? So that means that's why your frequency is increased as a function of frequency, as a function of a spring constant. But now, assuming we use the same spring, but now you increase the mass attached to the spring. As the mass of the object increase, what happened? Once you release it, it will move slowly back and forth, right? Why? Because it's a heavy, simply, right? So the frequency is inversely proportional to the mass. Right? So now let's think about this question. We have two identical blocks oscillate at a different horizontal spring, right? Which spring has a larger spring constant. And then just, you can forget about what we just did, right? So then which one has more frequency? This one requires shorter time to move back and forth. So this one requires longer time to move back and forth, right? For one period, right? So the answer is a red one, right? Even though you don't remember the formula, this one, right? You can also conceptually solve it, right? So just have a, you know, strong spring, we move back and forth quickly. So that's why the answer is A. Then how about this? A block of mass M oscillates, and then T is a 2 second. If a second identical block is glued to the top of so now everything same, except you just add one more mass. The new period will be increase, of course, right? Because you have a, you know, heavier one, it will move slowly back and forth. So the T must be shorter than previous. I'm sorry, the T will increase, right? Because it moves slower, right? So the answer must be either T or E. But now question is how much, right? So then now you have to approach this question mathematically. Again, how do you find the relationship between frequency and the decay? So again, you have to use energy conservation, right? Maximum E total, AL equals what? Maximum potential energy equals what? Kinetic energy max. So maximum potential energy is 1/2 times K A squared. Maximum kinetic energy is 1/2 times mv max square, where mv max is what? 2 pi f square. So you cancel also 2 pi f and a, right? So you cancel 1/2, 1/2. You cancel a square. So then now you see k is 2 pi f square, right? Divided by m, right? So again, 2 pi f is a root 2 k over m. Your f is 1 over 2 pi root 2 k over m, right? This is what we got here. So again, you gotta practice, this process a couple of times whenever you see this type of question. So then now we are talking about the period, not the frequency. So you have to change this equation for period. which is reciprocal of frequency. So this is a 2 pi root 2 m over k. So if you increase mass 2 times, T is proportional to root 2 m. So the answer is root 2 times 2. So the answer is D. Again, remember your frequency is 1 over 2 pi root k over m. And another one. So a mass of oscillate on a horizontal spring with a period of 2 seconds. If the amplitude of oscillation is double, the new period, again, I'm recommending you to drive this process again, E total. I'm doing by myself a couple of times, so you got to do this one as well. Is what? Potential energy max, kinetic energy max. So this is now, we can quickly do it. Ka square. Kinetic energy max is 1/2 times and V max 2 pi FA square. So now you see half cancels, AA cancels, and divided by M. So K over M equals 2 pi F square. So now you see 2 pi F is root 2 K over M. So F is 1 over 2 pi, right? So you can do it quickly. It is fast as well, right? So now you know the frequency is not functional amplitude, A, right? So the answer is C. It's irrelevant to the amplitude. Another one, a block oscillates on a very long horizontal spring. The graph shows the block's kinetic energy as a function of position. Now, your kinetic energy maximum is a joule, right? So your kinetic energy max is what? 1/2 times m v square, max square is what? 8, right? So then again, m v max is what? 2 pi f a square is 8. Then the m is not shown here, right? But now we know what is the maximum here, right? So x is 2, so a is 2, right? So then you can say 1/2 times m 2 pi fa square is 8. So then a is 2. So you can solve it, and then I'll recommend you, or you can solve it, right, using the kinetic energy maximum as well. So then here you have a joule 1/2 times Ka square, right? This is easier to find K only. So then your K is 16 equals Ka square. A is 4, so K is 4 as well, right? A is 2, sorry. Right? But also, again, you can use kinetic energy maximum as well to find the frequency here. And then after you find the frequency, you can use the relationship between frequency and the K, and then you find the K as well. But I believe this method is easier. And next example, you have a mass oscillates up, down. So again, simple harmonic motion. The motion is here. So lowest point and then highest point, equilibrium position, right? At which time the acceleration 0. Again, we think about, this is a kind of the question that you learned the last time, right? So assuming you have a spring, when do you have a, maximum velocity at the middle point? When do you have a maximum acceleration at both ends, right? Why? Because the force is kx, right? Minus kx, right? So that means when x is maximum, your force is maximum. So your acceleration is maximum as well, right? So the number one, the answer is A, C, E. A, C, E. At the middle point, acceleration 0. There's no force. And then kinetic energy maximum, again, is E, right? The velocity is maximum. And then potential energy maximum, PD, right? At both end, right? Maximum compression or maximum stretching. And then we have 4 different masses, 100 gram, 200 gram, 300, 400, from the identical spring. So that means K constant for all of them, which is unstretched. The length is 10 minus 10 centimeter, causing the spring to stretch, right? Stretch. Now, each mass is pulled down additional 1 centimeter. So now you start moving back and forth, up, down, right? And released so that it oscillates up and down. Which one has the highest frequency? Again, frequency is proportional to what? If you use a stiff spring, the frequency will move back and forth. Heavier one. So even though you don't, memorize the formula, you can roughly know this relationship, right? So now they use the identical springs. So that means K are the same. So the heavier, less frequency. So the answer is A, right? Because you're looking for the highest frequency, right? So you need the smallest m value to have the highest frequency, right? And the second one, now we have the same mass, right? From 4 springs, so now K is different, right? Which one has the highest frequency? Again, the same question, right? Your frequency is proportional to root 2 K over M. Here, M are the same, so your frequency is simply proportional to K. So then now you see, without knowing any physics, you can actually find which one has a stiffness, stiffest spring. Of course, A, right? Because once you attach the same mass, it stretches minimum, least distance, right? And finding the frequency of a mass hanging from a spring. This we did a lot this. So you attach a spring, is stretched by 5 centimeter, and then this is now in equilibrium position. So now you have a force upward, spring force upward, and then downward weights are the same, right? So then I think with this textbook doesn't explain properly, fully. So your net force is what? Spring force is acting upward, so it's a positive, which is a K delta L or Kx, right? And then the weight is a downward mg, and this is a 0. So your K is mg over delta L, right? So this is mg delta L. Again, you have to convert every unit to mks, right? So K is a 4.5, 4.9, or 5 Newton per meter, right? Now we know the spring constant, and then the second question here is what is the frequency again, right? And again, you must be able to find this equation. Again, how? I'm going to do it one more time real quick. K A squared, this is maximum potential, 1/2 times m v squared, which is 2 pi f a squared, right? So cancel, cancel, a cancel, a cancel. So that divided by m, so you have k over m equal to pi f squared. So your f is yeah, right? You see how quickly you can do it? And the last question, the pretty similar question, we have a 5 kilogram mass is suspended from a spring. Pulling the mass down by additional 10 centimeters. So that means your A is 0.1 meter, right? And then take the force 20 Newton. So now you see, A amplitude, and then the force. So you probably can find the K, right? If the mass is then released, it will, oscillate up, down. And then how long will it take for the mass to return to its starting point? So basically, you're looking for T, right? So then now spring for constant is 200. How can you know that? because the force F is K, X is a 0.1 10 centimeter, right? So your K is a 200 Newton per meter, right? And then amplitude is again 1.1 meter. The question is about the period, right? So your period, again, you got to do 1/2 times K A square is 1/2 times mv square, or 1/2 times m, 2 pi f square, right? Believe it, now you can do real key, right? A is A cancels, right? Your frequencies, you remember 1/2 pi root 2 k over m, right? So your period is what? 2 pi root 2 m over k, right? I think the solution use omega, but the omega is the same. So now you have a mass 5, 2 pi, mass 5, k we have 200. So then you can, if you calculate it, you will see t is gonna be about 1 second. Okay, that's it. Next time we're gonna talk about, pendulum motion. And again, let me know if you have any question. I can organize a Zoom meeting anytime you want. Thank you.